So now that we've tried these practice ones, I'm going to give you one more. Let's do the Red Devil resistor. 666. Let's do our 66 mega ohms. What does that mean? It's 66 million. There we go. That's a fun one. It's a lot of 0 ohms. It's the Red Devil resistor. 66 mega ohms. 666. 66 million ohms. How would you do it? How do you represent 6? The first digit is a 6. It would be blue, blue. Oh, and blue again. That's kind of ironic. It would be a triple blue band. Wow. And then, yeah, it's got to be gold because we're Red Devils, right? There we go. So in other words, doesn't matter what country you go to, you can buy the right kind of resistor depending on your application that you need using this color band. What's crazy is if you work enough with electronics, you actually memorize this after a while. You just kind of know it. So in college, I actually had this all memorized. Now I have no idea. I just have to look at a chart. So on a quiz or test or homework problem set, we wouldn't expect you to memorize this. But if I told you that it's orange, orange, brown, or green, blue, brown, or you should be able to figure out how much resistance is there. We're going to draw a schematic for a diagram that has 2 batteries. Let's go ahead and highlight what we need to put in our circuit with a single light bulb and an ammeter to measure the current. We're going to record the current flowing through the circuit directly on the schematic diagram and then on the equipment diagram. So the first thing we're going to do is we're going to draw a schematic diagram. What's that? It's a fancy word for a picture of what we're trying to build. You always start with the battery, the source of power. So the battery, the symbol is, if you don't remember, it's a short line and a long line, like so. I'm going to do little dots to represent the idea that we're making connections on each end. So we have how many batteries? We have 2 batteries. And it's a short line and a long line. And if you recall, the long line is always the positive side. The short line is always the negative side. That's the symbol for a battery. And I like to draw it so that the batteries point up. Why? Because we're going to use the gravity analogy. That the charges get pumped on an electric hill, and then they can flow down that hill and light up a light bulb, power circuit, all that good stuff there. So we're going to have it point up. And theoretically, these are 1.5 volt batteries. This would be 0 volts down here. This would be 1.5 volts. At the top of my hill, this should be 3 volts up here. Theoretically, would be a way to picture it. Let's complete our circuit. Next, the current can flow next through what? A light bulb, right? You guys remember the symbol for a light bulb? It's like a resistor or a curly resistor with a circle around it represent the evacuated bulb surrounding the filament. There's 2 connections there, right? And then we have an ammeter. What's an ammeter measure? Amps, exactly. And to complete a circuit, you always have to bring it back to the what? To the start there. Now to make your life easier, this is a little trick. We are going to label the positive and negative ends of each circuit element. What do I mean by that? Really simple. This is the positive end of my light bulb because this is at a higher voltage. It's not positively charged, but it's at the top of that electric hill. It's at the 3 volt side. So the job of the battery is to pump the charges up. There we go, this electric hill. Oh, climb the hill. There we go. Except I got a crazy seal right here there. It's going to flow down that hill and not kill everybody there, right? And it can do work there, right? We're going to use that gravity analogy. So anyway, current then is going to get pumped up this way. The conventional current, I, is going to go in a clockwise direction. I is the flow of, current is the flow of positive charge, conventional current. What's confusing is in real life, it's electrons that actually drift very slowly through a wire. But when we first defined electricity, like Benjamin Franklin and other scientists, they just defined it as a flow of positive charge. Now we know that it's the electron that drifts. But if the electron goes one way, it leaves a positive hole going the other way. And the net effect is, it actually isn't even the flow of electrons, because electrons actually go really slow through a wire. It's the flow of energy delivered by charges. It's like a water pipe. When you tilt the water pipe, the water starts to flow instantly, but it takes a little bit longer for one molecule of water to get from one end to the other end. But pretty much as soon as you flick a light switch, it's instant. So now we'll go ahead and label the negative end of the light bulb. That's underneath. The positive end of the meter is on top, and the negative end of the meter is on the bottom. Now you might say, well, gee, I don't get this. How is this helpful? The point is to be able to now translate English, that's what we first did, into a picture, schematic, and in real life, you don't want someone to build like a computer by reading this like book and then trying to build it. You want to look at a diagram so you don't have any mistakes. But now we're going to translate it to something concrete. How do you actually build it on the circuit board? Your diagram is already better. I think we already labeled this one as battery number 1, this one number 2, because there are 2 batteries. The positive terminal is on the left and the negative terminal is on the right. So now, how do you know how to wire your circuit? We're literally going to translate. Parlez-vous français? Guten Tag. Here we go. We're going to translate our schematic into our circuit diagram by tracing the flow of the current. So we always start at 0 volts. The job of battery number 1 is to pump up the charge. Yeah, I will pump you up to a higher potential. Going from battery number 1, from the positive end of battery number 1, we go to the what? The negative end of battery number 2. You see that? That's where the first wire is going to go. Then from the positive end of battery number 2, we get pumped up, to 3 volts. We go to where? The positive end of light bulb number 1, right there. And on your diagram, we like to call this the positive end of the light bulb, this the negative end of the light bulb down here. And do light bulbs really have a positive negative end? The answer is they don't. But we like to use the gravity analogy. That just helps us picture what's uphill, what's downhill electrically. The current will now flow through the light bulb. It'll lose some voltage, some energy. And then from the negative end of the light bulb, we go to the what? The positive end of the ammeter. What the heck is an ammeter? It's something that will measure amps. So on your multimeter, let's draw it on the side. It's not on your circuit board. Let's draw how you hook up your ammeter. So how do you tell your multimeter to read amps? Literally, you have to set your dial and you set your plugs. So how do you tell the meter to do amps? You guys remember? You turn the dial to what? To the 10 amp setting, because we're reading larger currents. That's at about the 4 o'clock position on this meter. The black plug always goes in the middle. Where should the red plug go? On the left or right? On the left in the 10 amp DC connection. On the left here. Label that so that you don't mess that up there. So from the negative end of the light bulb, we're going to go to the positive end of my meter. And then I'll get a reading in amps, which I'll record on my diagram in a second. The current flows through the meter. And then from the negative end of the meter, we go to the what? Negative end of battery number, which one? Battery number 1, right there. So literally, I am translating wire by wire exactly my schematic into an equipment diagram. Now I can build this with 100% success. Let's try it. So you always start from 0 volts, get pumped up, to 1.5 volts, Then from the positive end of battery number 2, we go to the negative end of battery number 1, pump up to 3 volts, ideally. Now what? Let's translate our diagram, right? We go from the positive end of battery number 2 to the what? Look at your diagram. To the positive end of the light bulb, right? Light bulb number 1. My meter, I set to 10 amps. Black plug is in the middle. Red plug. Oh, is my red plug in the right place? No, you will not get a reading if you do this. And then I had another group where the dial was in the wrong place. They didn't get a reading, and their light bulb didn't turn on. It was so sad. Every little wire needs to be in the right place. Every little wire, every little setting. Next, red plug is on the left in the 10 amp side, because it's literally a different circuit. Then I go from the positive end, or the negative end of the light bulb to the positive end of my meter. From the negative end of my meter, I go all the way back to ground to complete the loop. And if all goes well, yes! Let there be light. And there was light, and there was much rejoicing, and everyone was happy. Yay. How many amps am I getting flowing through my circuit? 0.26. It'll fluctuate a little bit as you run the batteries down.